Good afternoon to everybody. I'm not Sébastien Vincent-Bonnier, but I will be chairing the session. So we start with this session, which is about the two FDT proposals that we have in the fundamental physics domain. The first one is on atomic clocks. The second one will be on ultra-cold atoms. And then I invite the first speaker, Stefan Schiller, from the University of Düsseldorf, and he will tell us about the atomic clocks FDT proposal.
Hello, good afternoon. Thank you very much, Luigi. I'm pleased to be here and to be able to report to you on the work of one of ESA's facility definition teams. I acknowledge all the members of this team that are listed on this slide, and I acknowledge also Luigi, who has been the ESA scientist on that. And this slide essentially shows what the ISOC Pathfinder mission is about. It's supposed to compare the tick rates of clocks on the ground. This comparison can be in common view, as shown here, or in non-common view, meaning that the two clocks will not be interacting with the space station and with the ISOC Pathfinder instrument at the same time, but delayed in time. And the function then is more specifically then to compare the frequencies of different clocks and to synchronize them. And these clocks can be essentially anywhere on the Earth. Well, they have to be at least part of the time in the visibility range of the space station. We can have two different scenarios. One scenario can be where two clocks of extremely high performance at different locations on the Earth are compared with each other. This has applications in fundamental physics and geodesy. Another scenario is where one clock is an extremely performant clock and the other one is a much less performant clock, and then signals from the performant clock are transferred to the other clock, synchronizing it and stabilizing it. So here, the reference clock serves users distributed all over the globe. And of course, the goal here is to achieve a performance that is beyond the current performance of clock comparison techniques via satellite, and also better than the near future approaches, specifically what the ACES mission will achieve. We've heard about the ACES mission yesterday in Christoph's talk, and so in a sense, ISOC Pathfinder is a follow-on mission to ACES. So more listed here are the science topics that ISOC Pathfinder will address. Fundamental physics. So this is the domain where one tries to find answers to some of the key questions in physics today, like what are the ultimate laws of nature? We don't know them yet because there are surprising discoveries that have been made, such as the existence of dark matter, dark energy, and so on. There are puzzles that we have observed in the universe. And so there are good reasons to try to understand in a more detailed way the foundations of physics. And here, the comparison of very accurate clocks on the ground can play a role. Another field of application is to do geodesy, to serve geodesy by mapping the geopotential of the Earth with a novel technique called relativistic geodesy or clock-based geodesy. And this can be done in the near future and with ISOC Pathfinder with an extremely high effective resolution in the gravitational potential, corresponding to 1.5 centimeter height. ISOC Pathfinder can also support the further development of space geodesy. And then a general purpose application is what I just mentioned, that it can synchronize clocks worldwide to a high level, and it can transfer very stable frequencies also to a large number of users that do not have such frequencies available, and they can use them for general purposes in science. So at the basis of this mission is actually the ground segment, which is a large number of laboratories today that own, operate, and further develop atomic clocks of highest performance. These are today optical clocks, in the near future even nuclear clocks. A partial list of institutes and groups is shown here on the right-hand side. And most of these laboratories do require to compare their clocks with other clocks. This enables the fundamental physics goals that I mentioned earlier. And so a link between these clocks is really needed. In certain regions of the world, this link can occur via a fiber optical network. Example, Europe, Japan, China, but this cannot be done everywhere. And these links are also very costly to maintain. And these links certainly will not be sufficient to do extensive geodetic campaigns that should really cover the whole surface of the Earth. Let me give you some examples of these goals. First, let's start with fundamental physics. And as we've heard elsewhere in this conference, the equivalence principle is the foundation of Einstein's general relativity and continues to be of interest in testing it, in the search of a more fundamental theory that encompasses both gravitation and the atomic forces. And a novel type of the equivalence principle can be performed in the way that is sketched here. And maybe it is good to mention how the equivalence principle will be tested in the ESA mission. There one will study the gravitational redshift of the clock tick rate in the gravitational field of the Earth by comparing a clock higher up in the gravitational field with ground clocks. But here we're considering clocks that are in the gravitational field of the Sun and of the Moon. The Moon is not shown. And consider two situations that follow each other in time. In the bottom situation, we see two clocks on different continents that are at a certain point in time at the same distance from the Sun and the same gravitational potential of the Sun, and so presumably have the same gravitational redshift, the same tick rate with respect to each other. But a quarter of a day later, the positions have changed and the gravitational potential of the Sun at their locations will differ. And so their relative tick rate will also change. And this relative tick rate could be measured with the help of a satellite mission, such as ISOC Pathfinder. So following the relative tick rate over many days, weeks, and months, one will be able to measure this varying relative gravitational time dilation, between the two clocks. However, it turns out that this is actually a null effect because the Earth is in free fall around the Sun. So it's actually an effect that in principle is there, but then is canceled. And so a null test of the equivalence principle for clocks in the gravitational field of the Sun can be performed if we have a way to compare distant clocks using satellite techniques. Similarly, this test can be performed by taking into account the gravitational field of the Moon. And the two principal science objectives listed there give the estimated uncertainty in these tests. Another very important test of fundamental physics is to search for a possible interaction between dark matter and normal matter. It is not known how strong this may be. There are only upper limits given by observing phenomena in the universe. But if there is such a coupling, then this could lead to a variation of the fundamental constants of normal matter in time. We don't know how large these variations can be, nor at what frequency they occur. And so we need experiments to search for these variations, maybe to discover them, or at least to bound them. And this can be done, again, by the comparison of clocks. Clocks that are dissimilar in nature, for example, composed of different atoms or different molecules, will have tick rates that oscillate against each other as a function of time if such a coupling to dark matter exists and has the right form. So we need to compare dissimilar clocks or clocks located in different locations on the Earth, or even clocks on Earth and in space with each other over extended amounts of time. And the more clocks we have, the more sensitive such searches can be. The second important science case for ISOC Pathfinder is a new type of geodesy. In geodesy, one seeks not only to measure the topography of the Earth's surface, but also to measure the gravitational potential at different locations in the Earth or on the Earth, and also its time variation. And the important concept here is the geoid, which is an imaginary surface that extends into the landmass according to the gravitational potential value defined by the mean ocean surface. So it's the red line. Now, topography and geoid surface do not correspond, and one typically wants to know the height h above the geoid for a particular location on the Earth's surface, r1, or equivalently, the value of the gravitational potential u at that point relative to the arbitrary definition of the potential of the geoid uc. Now, the classical way of doing it is to take a gravimeter that measures local acceleration and then to transport that from a reference point on the geoid all the way to the observation point, integrate the signal, and then determine the difference in gravitational potential. But this method is not accurate. The uncertainties add up for each measurement, and so alternatives had to be developed. And one very powerful alternative is satellite gravimetry. Here, the force acting on a pair of satellites leads to changes in the relative position that can be monitored, and then it is possible to produce such beautiful maps of the overall gravitational potential of the Earth. So the method is successful, but it has some disadvantages. It takes a lot of orbits of the satellite pair around the globe to produce such a map. The spatial resolution is low because the satellites are obviously high above the Earth's surface, and there are inaccuracies and a question of bias and so on. So definitely it's of interest to look for an alternative technique. And this is where relativistic or clock geodesy comes in. This is completely complementary, and it's based on essentially Einstein's theory of general relativity. This consists in placing a probe clock, an atomic clock, at a position of interest, R1, and comparing its tick rate with a reference clock placed on the geoid. The comparison of the tick rates or frequencies can be done anywhere. It could be next to one of the clocks or in space where the green point is. And from the ratio of the measured frequencies, then one can infer, in this equation on the left-hand side, the difference in gravitational potential. So we then have the possibility to map out the gravitational potential, and in a very local way, because the clock has a very small extent and is located right next to R1. Plus, with the appropriate technology, this measurement can be done within a day, and so we could have high time resolution if we repeat the measurements for months, and we can look for seasonal variations of the gravitational potential due to changes, subsurface changes, for example, in the water table. So this method is completely different than the other, more mechanical methods. Now, it relies on the availability of ultra-high accuracy transportable clocks. And these are now coming online. They're becoming available. And you see here 3 of several examples. These are the most advanced examples to my knowledge. On the top right, you see a trailer built by the German Metrology Institute in Braunschweig that contains an optical lattice clock based on strontium. And in the lower line, you see 2 clocks from a Japanese research institute. On the bottom left, you see a clock that is transported in a packed way and then unloaded and placed in a laboratory where it can be operated quickly and be used to measure frequencies. And the second bottom panel on the right-hand side is an even more advanced transportable clock that's permanently operated within a van, a special van, and it's completely self-contained and can travel essentially anywhere on the Earth's surface. These clocks have already been transported within Europe, from Japan to Europe and back, and in Japan, so this really works. Their fractional frequency uncertainty is in the mid 10 to the minus 18 range, and it's expected that this will improve over the next years. Another to show how this works, here's an example where the transportable clock in the vehicle, shown on the top left, is compared with another clock in a laboratory. And the relative tick rates are studied. This turns into a relative, or in an absolute or relative frequency difference that is shown in the right top plot. It's the blue line. And the two clocks that are nominally identical show a slightly different frequency. Here it's just 0.2 hertz difference. And this 0.2 hertz reflects, in this case, the gravitational potential difference between the laboratory clock shown in the photograph and the van clock. They are at a height difference of 5 meters, and that's how this frequency difference arises. And the impressive thing about these particular clocks is that their stability is so high that they can integrate down and be sensitive to fractional frequency changes at the 10 to the minus 18 level, bottom right plot, within a few hours of integration time. So from this we can see that these measurements have the potential to be also very fast. And so considering having one such clock on a van in a campaign lasting 1 year, it could easily perform 100 measurements and therefore cover a good part of a continent, actually. A further aspect is that these very high performance clocks are now being turned into commercial systems. These photographs here show the result of a Japanese academic industrial corporation that has developed a lattice clock that has a volume of only 250 liters, a power consumption that is probably at a similar level numerically in watt. And these clocks will soon become widely available, it is believed, and therefore be usable by different research groups, either in fundamental physics or geodesy groups or other users. So this is a very important ground segment aspect of the ISOC Pathfinder mission. A third science topic that ISOC Pathfinder can serve is to enhance satellite geodesy. Satellite geodesy is performed in order to study the large-scale motion of the Earth, its rotation, its orientation in space. And this is done using special observatories, for example, this one here in the photograph in Bavaria in Germany, where a number of techniques are simultaneously applied, for example, a very large baseline interferometry, laser satellite ranging, SLR, and so on. However, these techniques have their limitations. They are radio frequency techniques in part. They suffer from temperature sensitivities, delays, and so on. And so novel forms of calibration are necessary to improve these techniques. And it turns out that with the help of optical atomic clocks, a major performance enhancement could appear. So it's of great interest to place optical atomic clocks at these stations and then be able to compare atomic clocks at these stations with each other in a fast and reliable way. This opens up new possibilities in this particular field of research. So summarizing, ISOC Pathfinder has the goals of synchronizing ground clocks, both clocks that are in common view and non-common view at the level of a few tenths of picoseconds, and also to compare the mean frequencies of clocks in a fast measurement, as I mentioned, on the timescale of a day, at a level of 1 times 10 to the minus 18, so a level compatible with the performance that we can expect within a few years from a large number of clocks on the ground. This mission is very timely because the ACES mission has a finite lifetime until the end of 2027 approximately, so we need to have a mission that fills the time afterwards. And it should also be clear to all of us that in China there is a very strong program concerning time and frequency metrology via space. They have developed already several of the ideas that were developed in the framework of the ACES mission, and they work, and they are continuing this work, and Europe should not fall back on that. The strategy of ISOC Pathfinder is to really build on all the work that has been done within the ACES mission. Major, massive work and major expenditures have occurred. This should be reused and further developed. And by doing so, the timeframes will be much shortened. We can rely on high TRL of several devices and make this mission into a very powerful one, but is also possible at a reasonable cost and with very low risk. And as I said, essential is the ground segment, and here one is profiting from the stupendous developments that were done in the field of quantum technology over the last 25 years. So now let me go on to some technical details. Here's the schematic of the ISOC Pathfinder instrument that I said can be operated on a space station, but it could also be a satellite. It might even be more advantageous to have this on a satellite with a more appropriate orbit. And the ISOC Pathfinder instrument contains two types of links. Left in green, the microwave link, and yellow, it's a pulsed laser link. And these are supposed to compare tick rates of clocks or synchronized clocks on the ground. Here, the common view modality is shown, but this shall also work for clocks not in common view, i.e. on different continents, for example. And then to carry the information about the tick rate of one clock over to another side of the Earth, we need a local oscillator on board of the satellite, and a good choice for that is a hydrogen maser. The two types of links are shown again here. On the left is the microwave link. This will work necessarily by using radio antenna. So there will be a microwave antenna on the instrument in space, but also the ground users, the ground clocks, will need their own antenna. These are satellite type antennas. And as I said, one of the scenarios is to compare two transportable optical clocks in trucks, or one transportable optical clock with a reference clock near the sea, or with a National Metrology Lab clock. Another scenario would be that the national clock of extremely high performance serves to synchronize a clock at a user facility, for example, a university, which otherwise wouldn't have the opportunity to install a high-performance clock. On the right-hand side, we see the optical link. So here, again, in principle, common view comparisons are possible, but more interesting are the non-common view comparisons, because these are to be done essentially between laser ranging stations. These are expensive, big stations available only at a more limited number of locations, and these are geodetic stations often. And so the non-common view modality is here extremely important. And this works then by using lasers. Here are some numbers concerning the specification of the links. ISOC Pathfinder is designed to serve the optical clocks that will become available in the next years, as I said. So we're interested in comparing clocks to the 1 E-18 level over an integration time of a day. That's the third line in this table. This can be achieved with a future microwave link. With an optical link, this can also be achieved, but a much longer integration time is needed. The ability to synchronize clocks is similar in the two techniques. Of course, a difference is that the microwave link can work also in cloudy weather, while for the optical link, one needs a free line of sight between the ground station and the satellite. And in the bottom line, we see the specification of the ACES mission. We've heard yesterday in the talk about the tests of the performance of the microwave link, and that performs very well already in the testing environment. Here, the frequency comparison is specified to be 1 E-17 in 4 days of integration time. So you see, ISOC Pathfinder can have an improvement in sensitivity here by at least 1 order of magnitude. Let me briefly go into these link types. First, the laser link. It's a bit simpler to understand. The laser link essentially works with pulses. So the idea is to synchronize a clock in space as a local oscillator with a clock on the ground. The clock on the ground, say, emits a laser pulse when it's noontime. This pulse travels to the satellite, and when it's received, it tells the satellite clock to set its clock at noontime. This is the basic principle already envisioned by Einstein, but in practice, the distance between the ground clock and the space clock is not known in great detail and is also varying in time. Therefore, it is necessary to implement this optical link as a two-way link so that this propagation time is actually measured. And for that purpose, part of the laser pulse is reflected by a laser retroreflector at the satellite and sent back to the transmitter station. That can measure the propagation, back and forth propagation duration, and take half the value and correct for that in order to determine the proper synchronization time. This method works very well if implemented at a single photon level. That is, the laser pulses are detected with a detector that can register single photons, and that is taken then as a signal of arrival of the pulse. It's a digital signal, and this simplifies a lot the signal processing and makes it very stable. So it has been shown in extensive tests that this method can give a very high precision in time transfer over short times already, and also very good long-term stability. So it is foreseen that this can lead to clock frequency comparisons at the level of 1e-18 for integration times on the order of 10 days, and also clock synchronization at the level of a few tenths of picoseconds. This technology is actually already space-proven. It's been implemented in the China space station a year ago or so. As I mentioned, the Chinese have a strong program in time and frequency metrology in space. On their space station, they have installed all the things that also ESA plans and will and wanted to install over the years, so different kinds of clocks. And in particular, there is also a laser time transfer system on board. You see in the photograph the laser reflector array. And the detector has been developed by Czech Technical University, the same group that could also provide the detector for the ESA Pathfinder mission. The time measurement unit is a Chinese version of what has been developed by CTU. So this system works very well in space and is established. It should be mentioned, I extend what Christophe Salomon said yesterday, that also within the ACES mission, a version of the laser time transfer will be implemented. This technique requires laser ranging stations, essentially, and it is planned in 2026 to compare two atomic clocks at two German laser ranging stations, Wetzel and Potsdam, to demonstrate this technique and to compare it with the microwave link technique. The status of the hardware development for the future link for ESA Pathfinder is given here. It's a relatively simple technique with only a few components. They already have very high TRL. It remains to turn the event timing unit into a space-qualified unit, but this can be done at moderate cost. The second type of link is a microwave link. This link is called HERO. It's a new development, follow on to the microwave link of ACES. In this case, one uses continuous wave microwaves, and then the synchronization between a ground and a space clock is not so obvious because a continuous wave seems not to contain any information. However, if this microwave is modulated appropriately in time, then it is possible to transfer timing, and this is exactly the approach. Again, this must be a two-way link because the propagation distance is varying and there are Doppler shifts, and so the actual technique, how to use modulated microwaves to do this in an optimal way is more complicated, plus there are the effects of the atmosphere, the electron content that can also lead to disturbing effects. All of this has to be taken into account. A lot of this has been done for the microwave link of ACES, but for ISOC Pathfinder, the performance is to be increased, so modifications have to be made to achieve that goal. And ESA has sponsored development studies performed by industry, Thales Alenia Spazio in Italy, and they have developed a prototype transceiver for ground and space use that is able to serve 4 ground stations. That's the specifications simultaneously. And it's a fully digital system with a high carrier frequency on the order of 30 gigahertz, a high rate of modulation that gives a high resolution. And the goal specifications here are, as mentioned earlier, to be able to compare ground clocks with a resolution at the level of 1 E-18 on a timescale of a day. A breadboard has been developed by the company, and you see here the photographs of the transceiver for space and for ground. They look more or less identical because these are breadboards. And on the left, you see a plot of an early characterization of the performance in the frequency measurement. In blue is a requirement. You see it goes down to 10 to the minus 17 at 10,000 seconds, and then would go down further to 10 to the minus 18 for longer integration times. And the measured line is shown in red. So it's already not bad compared to the specifications, and the limitation of this setup was that some technical details were not optimized, such as the local oscillators in the boards. In an upcoming ESA contract, the company will continue this development and will turn it into a robust system able to be space qualified, and it will make use of the technology it has developed for communications between Earth and the Moon. In the Lunar Gateway program, they developed transceivers for the K-band. It's the same band that the ISOC Pathfinder link shall work at. And you see here an EQM of that transceiver, and the same technology with modification can then be applied to implement the HERO link for ISOC Pathfinder. And this will be a development that can be completed with a delivery of an FM within approximately 2 years. So I need to speed up, I believe, here. The third instrument on board of ISOC Pathfinder will be the local oscillator that enables the non-common view comparisons. And here the idea is to use the space hydrogen maser developed for the ACES mission. This device has recently undergone the final tests for the ACES mission and has achieved a frequency instability of just slightly above 1 E-15 for integration times of 10,000 seconds, as you see on the left. And this is an excellent device to be reused, rebuilt, and then used on the ISOC Pathfinder mission. Finally, a few words about timeline and cost. A very rough estimate of the cost for the space instrument gives a cost below 40 million euro, including margin. This does not include the mission operation, the ground segment operations. A substantial cost will come there, but this is then in the main interest of the scientists in geodesy and fundamental physics. And it is believed that such a mission could be implemented within approximately 5 years. So to summarize, the main point is that ISOC Pathfinder is really a feasible mission because it's based on existing or nearly existing devices with high TRL. It's of moderate cost and of huge utility for the physics, geophysics, and other communities, for example, VLBI. It's timely because the end of the ACES mission is already in sight, and we have to plan for a follow-up mission. And we also have to continue working in Europe on time and frequency metrology with the help of space and not let the Chinese do everything. Thank you very much for your attention.
Thank you, Stefan. Time for questions. Christophe?
Well, this is a general question. With the timeline that you showed for the development, the ISS will not be available. So what kind of career do you hope to put ISOC on then?
Okay, it's an open question when the ISS will stop being available.
Well, it will
Yes.
come, right?
So,
it would be a shame to launch ISOC for only a year or two, right?
Well, it still would be valuable because, first of all, I believe there will not be such a long commissioning phase once it's in space. And with the high performance of the microwave link, one will still be able, given the large number of clocks on the ground by that time, do a lot of measurements. So even an experimentation of 1 year would be quite valuable. Of course, eventually the community would like to have a permanent installation space, but that's for the future. So, as I said, a space station is definitely not the only option. It could be a MEO orbit, a HEO orbit. This could be a piggyback for another satellite. So anything is fine. This does not need to be a drag-free satellite or anything as complex as that. So we hope to find an accommodation somewhere.
Other questions? Okay, let's thank Stefan again. And Nasser is ready. Nasser Galul from the Leibniz University of Hannover. He will tell us the other FDT proposal in the fundamental physics domain, which is based on the study of ultra-cold atom physics.
Yes, welcome everybody. Thanks for giving me the opportunity and to present our results in this facility definition team of quantum science and atom interferometry. So I'm speaking on behalf of this list of many colleagues, actually, from quantum science. And as the experts of you would recognize, they kind of cover a large, let's say, range of physics that we can do with quantum science and atom interferometry. We were also very happy to be able to include colleagues from the US, since ESA was happy about this. So we included Jason Williams, who is the mission scientist of the Cold Atom Lab on the ISS, Tim Kovaci from the MAGIS collaboration, gravitational wave detection at the Fermi Lab, and Nathan Lundblad, who is a flight PI of Cal on quantum bubbles as well. So they gathered also quite a nice additional expertise here. And we were helped, of course, by Luigi as the study scientist and by Thomas Peignier as the system engineer from ESA. So what we would like to consider here and what we wanted to offer as a facility is something that comes in two flavors. One is fundamental quantum gas physics, so basically studying the quantum mechanics of effects that are really interesting and impossible to study on Earth. For example, quantum mixtures or mixtures in new topological states, like in quantum bubbles, like on a sphere, basically, or in uniform potentials, such as BECs in light boxes, etc. So this is like the first big axis that we wanted to propose here. The second one is, of course, traditionally what we are interested in, which is the metrology axis, which is looking for dark matter, dark energy, looking for shortcomings of the general relativity, basically, or the standard model, whichever comes first. And our way to look at that is to use, rather than clocks, to use atom interferometers. So atom interferometers, here is a short reminder about how it works, work like when you realize the superposition of states, basically of matter, and you could realize something like a Machtsander interferometer, and this Machtsander is then ready to read out the acceleration along the laser that you interrogate the atoms with. And through observing the phases, you are able to say something about this acceleration. If you add another species in the mix here, then you could realize a simultaneous accelerometry test, which is a test of the universality of free fall then, very automatically. And you could extract, actually, if the two species experience the same accelerations and put bounds on this and measure, for example, the ESA-HRE parameter. This is not the only thing you would look at if you are testing the universality of free fall, but that's a very strong first, let's say, parameter you would like to extract. Just for recalling it, the state of the art is nowadays with microscope. The microscope satellite is a classical test at the 10 to the minus 15 in the ESA ratio in eta. And the state of the art right now is with quantum tests in Stanford, which is the test of Mark Kasevich at 10 to the minus 12. So this is the second axis we would like to look at. So I'm starting here very quickly with the model philosophy, because I have to show this to you to understand what are the exact science cases that we aim to target here in this facility. So we would like to start in the very near term with a demonstrator. I will go into the details later, but this apparatus exists right now. It is a heritage basically from a DLR mission, which is integrated in an Einstein elevator in Hanover right now. So we could start testing and demonstrating things for this facility about that. Then in the meantime, what I call breadboard that could later be transformed into an engineering model should be built. I'll also go into the details of this. And this will have the additional, let's say, feature of being modular. So there will be one, let's say, source chamber that you see on the left that would be the same for all science cases. But then there will be the possibility to attach particular science chambers that you see on the right to fulfill one or the other science cases to basically the ultimate performance. And this would be the same for the flight model, so I'll explain a little bit later the philosophy of the operation on that. I summarized here the science cases that we propose for the near term, and there will be also an update in the next slides for all the three phases that I talked about. So it is not something that aims to particularly realize basically a record for one of the science cases, but for all of those. And what I'm talking about here is something on the side of metrology, for example, inertial sensing. This is absolute inertial navigation, basically. It's having basically an information about the accelerations either in one or three axes of your spacecraft extracted out of the atoms. So this will be another way to navigate basically in deep space. We would, of course, try to do a test of the universality of free fall here for this model at the 9 to the 10 to minus 12 level. This will yield automatically some bounds on dark energy, dark matter searches that are not possible at this level of performance, but with the next models it will be possible. As I said, we will explore uniform density quantum gases, molecular physics, quantum gases on curved manifolds, for example, on these bubbles, bubble traps here. And we will also make tests of quantum mechanics, basically of spontaneous decoherence models by simply looking at the free expansion of a quantum gas for several seconds. So there are decoherence models that expect that there will be additional terms basically in the Schrödinger equation. And one could also look at limits of entangled atoms and cavity enhanced atom interferometry. So the same science cases will carry on, but with a better performance on the second breadboard generation. So we will reach, for example, the 10 to the minus 12 meter per second square in acceleration measurement. We will have rotation measurements to the 10 to the minus 10 radians per second. We will reach then in this intermediate model the state of the art on Earth for quantum tests in UFF at 10 to minus 12. And we will carry on all the rest of the science cases. In space, then we will break basically the state of the art in all science cases here. So either in metrology or in looking at the rest of the cases. In quantum mechanics tests, if we are able to realize a free expansion of 20 seconds, then we could reach basically and rule out completely the CSL decoherence model. I will give here a very specific example of how the tests or how the generations of hardware will bring in the UFF test only. I don't have the time to go case by case, but in principle we studied all of these cases. So as I said, we are comparing here the free fall of rubidium and potassium atoms. So the machines I showed are quantum mixture machines. Both are in the condensed states. And here you see the formula in basically the accuracy of the differential acceleration that we are measuring. And the first demonstrator that we have will be delivering for us basically within a free fall time of 2 seconds. This is the capital T that you see there, something on the level of 10 to the minus 13 in eta. Second model with more atoms in both species, like 10 to the 6 atoms, and slightly longer time at 1.5 seconds could deliver the 10 to the minus 12 eta, and if we are able to put the device, the flight model, on a free flyer or on a commercial space station, then we expect to reach the 10 to the minus 13, and it will be a question of platform later, but integrating down could basically even read us to 10 to the minus 15. All right, so this is how it looks like over the 3 generations for this science case. And what you see on the x-axis is the number of measurements. Keep in mind that one cycle time here is roughly 10 seconds, to which you will add the free fall time, which is for example, last model will be something on the level of, as I said here, of 10 seconds. So this will be a total cycle time of roughly 30 or 40 seconds. Okay, so that was the case, the science case here, the particular one. Let's go back to this model philosophy then to remind you about what I mean with the demonstrator. So I'll go a little bit more into the details of this. So this demonstrator, as I said, is basically a machine that safely flew to space on a sounding rocket last year. This is a DLR program that is ending right now. And it is, just in all modesty, the best in performance in numbers of atoms, the best machine that exists for a dual species BEC. So what you see in the red circle is the combined, let's say, performance in terms of flux. There are experiments that produce more atoms in a quantum mixture, but they are in time regimes that we are not interested in. So if you spend 50 seconds producing your sample, this is not interesting for atom interferometry. So we plan to use this. As I said, this is now being integrated in the Einstein elevator in Hanover. After we would have tried quite a lot of science with this, we would like to now make a step further and build what we call the breadboard here, which should ideally be built by the industry. So at least this is the cost estimate that we made here. And as I said, this will be the modular one. So the modular one, meaning that this, what you see on the left, which is the source chamber, this is something you don't touch. That's used by all science cases, and that's ideally operated in the Einstein elevator continuously, while other scientists would develop only their small science chamber, small or not, yeah, but it has to fit in the experiment later, and they can optimize it basically to their case. So if you need a UFF test to the 10 to the minus 15, then you need a 0.5 meter tube. If you need a cavity, then you build a cavity. If you need a test mass, then you build a test mass. So that's the philosophy here. And you don't bother basically with producing the BEC every time. And we even made the effort to study how we could integrate this in an express rack and include the express rack in the Einstein elevator. I'm going to tell you a little bit more about that later. So down there you see a budget in weight and power of such a device. And the flight model will look ideally the same. And what I have in mind and what we have in mind is that we would fly, for example, for a couple of weeks even, if this is how space activity is going to shift to, for one science case, and then the payload comes back, we just swap the science chamber, and it is then tested for something else. So most of the science cases do not need months of operation. Something on the side of weeks would be enough. And I hear that some of the free flyers or commercial space stations will have a lot of basically swapping and going back and forth to orbit. Yes, so I would like to say a bit of some words about this Einstein elevator, because this is kind of a central piece in our proposal here. So what you see here is a view of the inside of it. So the idea is that you have this gondola that you see down there, zoomed on the left side, which is mounted in this on the bottom of this metallic structure, and is actively accelerated up and down, creating a free fall of 4 seconds. So unfortunately, you cannot see the animation on this PDF, but it's an active drop tower, if you like, and it's an active drop tower that can mimic lots of conditions of space flight, like microgravity, but also moon gravity, Mars gravity, or any kind of hypergravity and tests on the boost phase. So it can do all of these gravities without any problem. It's located here in this high-tech building in Hanover, so it's really at the university, and yeah, as I said, it's an available facility that everyone could reasonably talk to the group responsible for that and just use it. Here you see some of the first tests, and you see on the left graph that it could realize the microgravity condition for something like 4 seconds, and that's what we are caring about here. I won't go into the details of that. A number of projects are being explored here. The whole tower itself and the elevator is an active research field, so the team there, the engineering team, is doing active research to make it better and better. There are some material science experiments going on. There are production technology for space research going on. And we have the two models of the payloads of two sounding rocket, MAIOS-1 and MAIOS-2, that are now there. And we start looking at atoms in microgravity in these space payloads. So yes, my colleague Christoph Lotz is the head of this research group, and I encourage you to talk to me or to him about future research. So here is a view of the MAIOS-1 payload, which is now augmented basically with a test mass for dark matter, dark energy, which is being now put on this platform and being shot to microgravity routinely every day. This is the same view of the experiment. There are a number of collaborations going on with NASA, for example, here to just simulate microgravity for these devices. As I said, we have a very recent engineering activity together with the JPL on integrating an express rack in this gondola. And the good thing here is that this gondola can take pretty much a ton and is not restricted in volume. and has 300 shots a day. So this is actually going way further than any other drop tower facility right now. So it's pretty unique, and we would like to promote this as basically a space kind of hub where everything that goes to space goes there first, is simulated. You have time to modify things, you have time to do statistics even, and before you send it. And yes, the study with the Express Rack is almost done, and we think that it's very positive. All right, so let's go back to our facility, basically, that would then be, in every model would be then operated in this Einstein elevator, and ideally there will be 2 copies, one on ground and one flying all the time, just to save times and costs. So this is the timeline that we came with. Here are 2 lines of research, one with alkaline atoms, which are the most TRL-ready species, rubidium and potassium. This is something that we've already seen in space. And there's another line of research with strontium, so which will take a little bit of time compared to it. So these are the first line and the second line on this diagram, and then you see so what will happen to the ISS then on the last one. The preliminary cost estimate is the first demonstrator is for free, almost, so there is no cost due to that. It is there. You can immediately start making science out of it. The breadboard will cost something like 10 million, and together, if it is updated to an engineering model, they will both cost around 40 millions, and a flight model would cost around 50 millions then. So this is our cost estimate of this. I would like to spend a few minutes talking about heritage and synergies with other projects, because that's very important that you realize that we are not starting from scratch, but we are starting somewhere where things are quite evolved. So we were pretty happy to be empowered by a strong national program by DLR about the Quantus and MAIOS missions. Our French colleagues had the ICE program with the parabolic flights, and of course the ACES experiment. Lately, we also were very happy to be part of the Cold Atom Lab, which is a NASA mission, but DLR got a bilateral agreement, so we are using this facility to. Just a few words about the different programs. Quantus started somewhere around 2004 with this drop tower first generation, which is called Quantus 1, which realized first BECs in microgravity, first interferometry in microgravity, etc. Then it was followed by this second generation. So what you see on the picture is the full experiment. There's nothing hidden there, no racks lying around. This is the experiment, and it has like basically a human size. And this has been dropped and catapulted, and could realize quite nice, let's say, records, for example, in slowing down the energy of expansion of the BECs to something like 38 pico-K in 3D. So this is what allows us basically to use these quantum gases for seconds. So we would be able to see them, no problem. And here you see a BEC after 2 seconds in the catapult on the bottom right, which is the one that was what we call delta kick collimation, kicked basically to 38 pico-K energy. And the MAIOS program, as I said, is the sounding rocket program with 2 models. This is the first one, which is called MAIOS 1, that you see here. I don't have time to go for details, but this experiment basically opened the era of quantum gases in space. So this was launched in 2017, realized the first BEC in space and the first interferometry in space on one basically parabolic flight. So it was a 6-minute mission, but it was a pretty successful one. And later, with the Cold Atom Lab, we had access to cold gases basically in orbit permanently since 2018 with the CAL program. And there has been a number of beautiful, let's say, science cases explored here. So here you see an astronaut unpacking the CAL experiment and installing it. And here you see a view of the first BEC that was realized. Last year, we realized quantum mixtures of rubidium and potassium. They are up there and being operated. And you could check the publications if you'd like to have more of an idea. Recently, we realized also atom interferometry, all of this in orbit and routinely done now every day through like the JPL operations. What will happen very soon is what we call the BCAL facility. This is going to replace CAL. This is now a DLR and NASA payload. You have a look on it right now here. And this will be launched in 2027. So this will be a very comparable machine to what I was telling you. So this is yet another iteration which will serve a number of science cases. So you'll see here the specs of what the experiment is offering, and you could check the publication down there for to know more about it. But it basically offers already a degenerate mixture of potassium and rubidium. Last year and the years before, there was a pretty intense activity in the US because NASA was working on its decadal survey, and we were very active there too with these American colleagues that I mentioned. And then the report was released. This is this Thriving in Space report, and we submitted also white papers for science cases and for facilities very comparable to what we were talking about here. And it was very helpful for our work in this ESA definition team because basically it was almost the same kind of science, and we are receiving a strong interest from NASA now for the ESA, let's say, efforts. So I hope this bilateral collaboration will go on. A few years ago, in 2022, we published this roadmap for ESA, and this was like a community effort. So this paper was co-signed by something like 250 scientists all over Europe and in the US, and we kind of explained what our priorities should be. And what you see here, you see the clocks, you see the Earth observation missions, you see fundamental physics missions as STE-Quest. And what we are talking about here is something that is basically a zoom in what will happen until the 30s. Unfortunately, STE-Quest, as you know, in M7 was not selected, so one has to update the date here shifted by 4 years, as M8 was just released, and we expect and we intend to submit STE-Quest again for the UFF test at 10 to the minus 17. In between, there were developments on the side of space quantum gravimetry for Earth sciences, so for geodesy, basically, and this is now an EU effort. So the European Union is pushing very hard to send a geodesy mission relying on quantum sensing to space by 2040. It is a priority, and they are pushing for a Pathfinder in 2030, so I have the pleasure to be a co-PI of this Pathfinder mission together with Frank Pereira in France. And this is, as I said, an EU effort with a strong involvement of CNES and DLR in the management. And the Pathfinder will be just a single-axis quantum accelerometer to show basically these performances and to show an absolute measurement of gravity in orbit with the same principle. So we will have here only one species, rubidium, made on an atom chip and interrogated by a laser field. And it's very useful to mention here that all of this is built by industry. So we are getting to a new step, basically, in these quantum gas experiments here to make everything robust and high performance. All right, and this takes me to my conclusion. So what we proposed in this FDT is a multi-user facility for quantum science and metrology. So this is not one science case, this is maybe something on the side of 10 science cases. We will have immediate science returns that if ESA decides to support this. So we will start next year operating the demonstrator in the Einstein elevator. It is there, it is ready for science, so we just basically need the cost for operations. And in the next steps, science will happen also at every one of them in 3 or 5 years, and then hopefully with a flight model. There was, in our model philosophy, we save a lot of time and a lot of costs by the modular operation. And we do that to challenge the state of the art, as I said, of these science cases. It is very well integrated in the landscape of missions, timelines, whether national, international, European missions that are happening here. It's using a technology that flew in space already, that showed the same performance we are talking about already. High TRL is there. So I hope I convinced you about all of this, and I thank you very much for your attention.
Thank you, Nasser. Time for questions. Christophe?
Thank you, Nasser, for this nice talk. In terms of Carioca, and what's the difference between what you can do in Carioca that you cannot do in Beccal? You see, in terms of measuring G. Can you comment a bit?
Yeah, absolutely. So Carioca is a satellite mission, or will be a satellite mission. So everything platform is very well controlled. So in Beccal, we can make these accelerometry measurements, and we will do, but it will be on the ISS. And the ISS is by far not the good environment that you would need in terms of vibrations. So it will not be. We are right now doing accelerometry measurements in Cal, but in something like 2T, 10 milliseconds, sorry, the signal is washed out. One can hybridize and make the effort on that, on hybridizing with classical sensors, but that's not what you would like to do for this absolute inertial measurements anyway.
So therefore, you impose a much stronger gravitational environment on board a dedicated satellite for Carioca.
At least for the Pathfinder, it will be a single-axis interferometer, no classical sensor, no drag-free, and this is expected to yield a performance around the 10 to the minus 9 meters per second square. So we would like to prove basically the power of the quantum sensor alone. And on the real mission, then the platform could be specified better.
Thank you.
Other questions? Okay, so then let's thank Nasser again. And with this talk, the session is over. Next step will be, I think there's a wrap-up session here later on at 4, right? Yeah, see you later.